And good morning, or good afternoon, and good evening. Thank you for joining us today. Today's topic, of course, is leveraging real-time behavioral insights that are gained from both Crank Software Storyboard and Percepio's Tracealyzer to really help you create exceptional user experiences on ST's STM32 MCU devices. So just before we get started, I just want to let you know that today's session will be recorded. So if you do need to drop off at any point in time, or perhaps you have a colleague that you feel would benefit from today's topic, we will be making this available on demand within the next couple of days. Also, because we do have a large panel of specialists on it, we will be having some Q&A at the end of the session. So at any point in time throughout the presentation, please use your question or your chat window that's on your screen to pose questions to the presenters. Also, if you haven't, feel free to follow us on a variety of social media, so whether it's LinkedIn, Facebook, or Twitter. And if you want to, during the presentation, feel free to do some live social engagements. Please use either the hashtags you see on the screen, or use all of them, whether it's GUI development, Crank Storyboard, ST Partner, Embedded GUI, HMI, and graphics. So speaking of our presenters today, we have the pleasure of having Mike Hartman, who is the product marketing manager at STMicroelectronics for both the microcontrollers and the microprocessors. We also have Johan Kraft, who is the CEO and founder of Percepio. We also have Gary Clarkson, who is the field application engineer here at Crank Software. And of course, there's me, Scott Snyder, who is the product marketing manager for our GUI development tool Storyboard at Crank Software. So just to kind of let you know how today's going to flow, of course, we're going to be doing an overview of the STM32 platforms. Then we'll jump into an overview of who Crank Software and what Storyboard is. And we'll pass things off to Johan. He'll talk about Percepio and Tracealyzer. And then we'll really dive into the demo portion and really kind of showing you how using the embedded tools found within Storyboard and then cross-porting them over to Tracealyzer really greatly simplifies the analysis of determining what's going on potentially with your GUI application to make sure that that user experience is exceptional. And then, of course, we'll jump into some live Q&A. So with that being said, I'm going to pass things over to Mike, who will start us off.
Hello, thanks for having me. As an introduction, I'm Mike Hartman, product marketing for microcontrollers and microprocessors in ST's Americas region. As technology evolves, a critical design challenge that must always be addressed is how humans interface with that technology. We call this the HMI of Things, HMI standing for Human Machine Interface. Graphics displays are all around us. We see them every day. And as embedded intelligence continues to grow, there are smarter and more connected products everywhere, addressing all markets from consumer goods and appliances to wearables, medical devices, and industrial. In the past, microcontrollers might have been limited to simple buttons for control and a segment LCD or VFD for display. Now we can offer rich touch interfaces with color LCDs and animations with smartphone-like control. The STM32 product portfolio and ecosystem possesses the technology needed for today's advanced graphics applications. You might already be familiar with this slide and our amazing STM32 offering. It shows our complete product portfolio and highlights our 10-year longevity commitment. We will use this slide to highlight the STM32 series with advanced graphics capabilities. Shown here are those STM32 products that possess graphics acceleration and other features. Starting from the top right, we have the STM32 MP1, our general-purpose microprocessor, which has an optional 3D graphics core. If you have a project that would run Linux or Android, the STM32 MP1 would be a good option to consider. In our microcontroller family, we have the STM32 F4, F7, and H7 in our high-performance product line, and the STM32 L4 Plus in our ultra-low power product line. All of these devices have graphics acceleration and other advanced graphics features. We will start by looking at the STM32 MP1 general purpose microprocessor. The STM32 MP1 can be used for a wide range of applications in a wide range of markets. Perhaps you are designing a medical device, industrial control, home security gateway, HVAC control, or a home automation device that's shown here in the picture. The STM32 MP1 can address the critical features needed for these applications. The latest additions to the MP1 family enables the dual Cortex A7s to be clocked at 800 MHz. This would allow the STM32 MP1 to support 720p HD video decode. When using the STM32 MP157 with the optional graphics core enabled, you can implement a high-performance user interface. And lastly, the heterogeneous architecture with both Cortex-A and Cortex-M cores provides the flexibility needed for various applications, including audio, voice, or other real-time processing. Now we'll shift back to the STM32 microcontroller options with graphics acceleration. We'll start with some of the latest news, and then we'll cover some of the core graphics technology. I wanted to highlight some of the latest additions to the STM32 microcontroller family with graphics capability. The STM32 H720 and H730 series were recently announced. These devices offer high performance and advanced graphics features. Additionally, there are flexible interfaces to support a wide range of external memories for both flash and RAM. The STM32 H7A and H7B series were introduced earlier this year. Targeted at graphics applications with LCD resolutions of 480 by 320 and below, the 1.4 megabyte of integrated RAM allows for an optimized design that does not require external RAM for your graphics frame buffer. Now we'll take a look at graphics accelerations and optimizations available on some STM32 microcontroller devices. ST's proprietary ChromArt accelerator allows the Cortex-M to be offloaded from graphics-intensive tasks. This includes DMA2D, which is direct memory access for graphics assets in Flash, the frame buffer in SRAM, and to the LCD. It also includes alpha blending and pixel format conversion. The short video here shows the benefits of ChromArt acceleration. As you can see, there are multiple layers making use of alpha blending. With ChromArt enabled, the typical CPU load on the Cortex-M is 2 to 10%. However, with ChromArt disabled, the CPU load will increase to 80 to 100%, and there is a visible difference in the performance. Select STM32 devices have a hardware-accelerated JPEG codec. This engine supports compression and decompression of both still image JPEG and motion JPEG. This allows for an enhanced user experience, possibly with a preloaded video without a performance impact on the core application. In addition to ChromArt, the STM32L4 Plus and the new STM32 H7A and H7B have Chrome GRC for memory optimization. Largely targeted at wearables and other consumer devices, Chrome GRC reduces the memory needed for the frame buffer of a non-rectangular display. Thanks for your time today. At this point, I'll hand it back over for the remainder of the session.
All right. So let's continue on here. So, as I said, my name is Scott Snyder, and I am the product marketing manager here at Crank Software. And so I just want to kind of just maybe set the stage a little bit. So definitely when it comes to developing UIs or GUI applications for today's embedded products, things have become increasingly more challenging. Definitely user expectations have been greatly elevated. Today, consumers expect an intuitive and modern touch experience, not only for the physical hardware, but the quality or the smoothness of the graphics that device provides. And this all has to do with having a powerful little embedded device in their hands every day that provides this rich experience. Also, the user experience has quickly become a defining part of today's products, with the GUI being one of the main factors that products are being measured on, and what often drives the value that consumers see in the product, and of course, ultimately their purchasing decision. And also integrating evolutions in technology no longer means only making hardware decisions, but how those hardware or those technologies can be incorporated into the user interface. And of course, the worst thing about it is that any time lost or any time resources are wasted or heavy coding changes that need to occur, these all create delays in getting the product to market on time and of course on budget. So Storyboard is really designed to remove the barriers and issues that are typically associated with GUI design and development. Based upon over 2 decades of experience in designing and implementing embedded GUI solutions for a broad range of industries, the founders of Crank Software set out to build a solution that would help remove the inefficiencies that often frustrated them and their colleagues when it came to developing UIs for embedded devices. And so, if you haven't heard about Crank Software before, I can definitely guarantee that at some point in time you've seen or have interacted with a product using a GUI application built using Storyboard. Our technology was created to help making that UI development easier on embedded products. Today's markets like medical, automotive, industrial, or consumer markets like wearables or white goods all share common challenges that we discussed before when looking to deliver that excellent user experience on the LCD. And so just to let you know a little bit about Crank Software. Crank Software is not only a software company, but we're also a services-based company as well. So that way we have a team of application developers that have a wealth of experience, so can help you at any stage. So maybe you have the design, but not the development know-how, or maybe you have the product you want to build, but not the bandwidth to do it, or maybe you're just looking to make sure that your UI is as tuned up as possible. We offer a wealth of services, so feel free to reach out to us at any point in time. Our leadership team has an extensive background in embedded graphics and systems with over 20 years of experience, and we have a large global customer footprint from Fortune 500 to small organizations, and have hundreds of millions of devices in the field running a UI built using Storyboard. So, powerfully simple yet sophisticated is what we hear quite a bit from our customers when it comes to them talking about Storyboard. Really, it makes it easy for them to create UIs quicker and more efficiently, and this is all done because of the architecture of Storyboard. And so it's a decoupled architecture that decouples the front end UI from the back end logic, enabling the designer and the developer to design, create, and develop that UI application in parallel. So it really makes it easy to get started early on the UI. Really makes it even simpler to embrace design iterations, and of course reduces the complexity of developing UI solutions in today's evolving embedded hardware, or maybe evolving product lines that you may have, really allowing you to faster time to market. So let me kind of break that down a little bit. So when it comes to accelerating development, so UI development can be fast-tracked by starting the UI design in tools such as Photoshop or Sketch, and once it's ready, can be imported into Storyboard. So from there, those files become the building blocks of the UI within Storyboard. And then those UIs can be brought to life using Storyboard's integrated animation tool that allows you to create, edit, and review animations all directly within the tool, as well as perform that critical usability testing and prototyping that really allows you to gain the stakeholder feedback earlier on in the design project, really allowing that project to move along quickly. And then, of course, the UI can be exported to a mobile device or a portable device for that portable hands-on user testing experience. So you can take it to them, as well as done on the desktop. So once UI development begins, though, the designers and developers can continue working in Storyboard in that parallel workflow environment that I talked about that removes the pain and the struggle associated with iterations. So let's face it, it's not a matter of if, it's really a matter of when, because when it comes to UI design and development, everybody has a particular viewpoint as that button should be bigger, that button should be smaller, that button should be over here, the text should be this color, and so on. So when you go out and you perform that kind of that usability testing, there's always going to be feedback that comes back, and Storyboard really makes it easier to embrace that. So you can easily introduce design changes without impacting the progress or causing a complete teardown of code. You can completely modify the UI look within, say, Photoshop or Sketch, and then re-import those design files without having to completely create an entirely new application or overwriting the prior development work that was done. And the beautiful thing is we have this unique tool or capability within Storyboard that really allows you to remain in control of those iterations. It's called graphical compare and merge, and so allows you to kind of like see the changes that were going to be done or proposed changes, allowing you to kind of choose all of them or pick and choose which ones you want to implement. So really allowing for a more efficient or organized workflow, and particularly when you have multiple users that may be spread out developing the project. And then, of course, even with the vast choices of operating systems and different hardware from MCUs to MPUs that you have, that Mike told us about, there's a good chance we run on it. And that's because we were created to be platform agnostic, which really allows you to de-risk your project by introducing a framework that easily supports technology and design changes at any point in the development cycle, really allowing you what we like to term UI flexibility. So it scales beyond just simple scalability, allowing you to scale up to an MPU from an MCU or from an MPU down, but also provides you portability, which allows you to switch out your technology stack, whether it's software, OS, or hardware altogether, allowing you to take advantage of specific board features such as graphic libraries, or maybe it's the introduction of a new H-series model that has more power with less price, allowing you to easily at any point swap that out without impacting the development. And then of course you have reusability, which allows you to take that GUI that you created for one project and apply it across different projects. So maybe you have a family, a line of high-end to low-end consumer goods that you want to have that consistent look, touch, and feel. You can easily do that with a Storyboard built UI. So what really makes Storyboard different? Well, Storyboard is not a code generation framework, right? So what it is, it's a foundation for that streamlined UI development for embedded projects. So we use a fixed point model that really allows you to decouple that front end from the back end, and which really provides you that UI flexibility that I just talked about. Definitely, we do have some unique features I mentioned, like the graphical compare and merge, which really enables your teams to remain in control of those UI refinements throughout the entire project, as well as we work extensively with teams at ST, at our partners, to really ensure that the Storyboard engine takes the most advantage of those specific board features, such as proprietary graphic libraries, or 2D or 3D hardware acceleration, or maybe it's memory management functions. So we basically take the hard work out of that. You don't have to worry about doing coding and compiling and tweaking and compiling, because our team of R&D experts basically have done that for you with our runtime engine. So you can guarantee when you marry up that engine with that specific board, you're going to get the most out of it that you could possibly get. And so with that being said, I'm going to hand things over to Johan, where he's going to talk to you about Percepio and Tracealyzer.
Thank you. My name is Johan Kraft. I'm the CEO and founder of Percepio. I'm going to tell you a bit about visual trace diagnostics with Percepio Tracealyzer. Tracealyzer provides visual trace diagnostics for developers of RTOS and Linux-based embedded systems. This allows for recording and visualizing the software at runtime. For multitasking embedded software, the source code does not give the full picture of the runtime system, which can be seen like a black box or the dark side of the code, if you will. Visual trace diagnostics gives you a detailed timeline of the runtime system and a large set of visual overviews, metrics and statistics. It allows for continuous live streaming of trace data from the target system to host, so you can monitor the system over long periods of time. You can even see live animated views of the data. As of October 2020, Tracealyzer supports embedded Linux and the following list of real-time operating systems. Streaming is supported for most of these platforms. In other cases, the recorded data is stored in a target-side RAM buffer, what we call snapshot mode. Software tracing is nothing new, but raw trace data is difficult to use in practice. Viewing this in a text editor isn't very helpful. You get large amounts of low-level events, where most are irrelevant repetitions of the same patterns. You can't see the forest for all the trees. To really benefit from software trace data in everyday development, the solution needs two more components. The data needs to be processed into a meaningful model describing how each event affects the system state. This requires the solution to understand all RTOS services that are traced, not just by the name, but what they actually do. The data needs to be visualized to allow quick intuitive comprehension and actionable insights, even for large datasets. The human brain is visual and excellent at pattern recognition, especially at spotting anomalies in repeating patterns. We can leverage that by showing visual overviews from different perspectives, such as graphs over CPU load or task response times. Finally, by connecting the views, we allow for a top-down workflow that is ideal for system-level analysis. Spot anomalies in high-level overviews and drill down to inspect the details. We call this visual trace diagnostics. This is useful for debugging purposes whenever you need a timeline for your software. This is often the case when debugging a full multitasking system, and especially important when the location of the bug isn't obvious from the symptoms, when the issue is difficult to repeat. Perhaps it only occurs once in a while for no apparent reason, or when interactive source code debugging can't be used, perhaps since the system can't be halted for debugging, or that you physically can't connect a debug probe. While many still use printf debugging in such cases, visual trace diagnostics is a superior alternative. The logging is much less intrusive, about 100 times faster than a printf over a serial port, which allows for logging much more information, also from the RTOS kernel. And the data is easier to analyze, even for large datasets, thanks to the powerful visualization. This means less debugging time and more time available for customer value creation. And with better ability to solve complicated bugs, you reduce the risk of project delays, or having to work 100 hours per week to make the deadline. Another important use of visual trace diagnostics is to find software design flaws. You have probably learned the hard way that designing RTOS-based software is quite challenging. There are best practices in RTOS software design, and these are important to follow. By design flaws, we mean deviations from these best practices. They are not necessarily functional errors, but they may reduce performance and responsiveness, increase the risk of future bugs, and make the system testing less effective. The impact on system testing can be especially problematic as it increases the risk of elusive bugs that leak out into production devices. This may occur if design flaws causes the system behavior to become less deterministic, more random, so to say. For instance, by introducing unpredictable variations in software timing. Complex and chaotic system behavior reduces the testability and may cause race conditions and other problems that may elude detection during the testing. Design flaws are important to find early, otherwise you might find yourself in debugging hell when the application grows, which may require a major redesign of the software. This is much more difficult in later stages of the project. The earlier you can find software design flaws, the fewer changes are required to fix them. With Tracealyzer, you can easily identify design flaws like excessive dependencies between tasks, unsuitable task priorities, and variations in software timing, so you can fix them early and avoid later problems. Last but not least, visual trace diagnostics can be used to measure software timing and resource usage. This way, you can verify real-time requirements and keep track of the software performance and resource usage throughout the development project. Tracealyzer provides timing metrics on task instance level, where you get a data point for each execution, each job of a task, such as task execution times, task response time, periodicity, etc. You can also define custom intervals based on user events that you add anywhere in your code, and then see the time between these events. You can even plot this data as shown on the right. And for all these properties, you can see the lowest, highest, and average values for each dataset. The highest and lowest values are also linked to the corresponding locations in the trace, so you can see the explanation behind these extreme values. Tracealyzer can also provide metrics on resource usage, such as the average CPU usage of each task, plots over memory usage, and the amount of data sent over an I/O interface. This way, you can ensure compliance with real-time requirements of your application, keep track of product performance, and find ways of improving it for a more responsive and capable product, improving customer satisfaction and sales. This can also avoid project delays by enabling early detection of any performance issues. In short, Tracealyzer is the leading solution for visual trace diagnostics and provides several important benefits. Easier debugging of system-level issues, finding software design flaws, and verification of timing and performance. This saves time and money by less debugging time, reduces the risk of project delays, improves product reliability and performance, and frees up developer time for important customer value creation. To learn more about Percepio Tracealyzer and how to get started with Tracealyzer on STM32 devices, please visit percepio.com/STM32. Thank you.
Thank you, Johan. Now let's pass things over to Gary.
Okay, thanks. I'm going to take you through the demo now. So what I'm going to do is run one of our demos. This is a coffee machine demo on the target board. I'll give you a bit of a quick overview of what that is. So we're going to be using the STM32 H745 discovery board, which has got a fantastic Cortex M7 core. In fact, it's dual core. There's an M4 there as well. We're not using the M4 in this application. So this has a 480 by 272 LCD panel and a touchscreen. What we've done, we've taken an application, we've added in our Storyboard middleware. This is our runtime library components, and the demo has been exported from Storyboard in the form of a header file, which we call a virtual flash file system. So this is our proprietary kind of assets layout, which we export in the form of a header file you add to your application. So this is the Storyboard project side of things. We're going to be using IAR, the EWI 8.50. With the STM32 Cube H7 BSP, which brings you the free RTOS and the Chrome art drivers, and we're going to be using that as part of the application. So we are actually working on the GTC platform, so the IDE, the STM32 Cube IDE currently. So that will be out shortly. But let me flip over to Storyboard, and I'll show you the application. So if I hit play, I'll show you it running first, and then we can talk a bit further through it. So the coffee machine, I don't know if you can see that. We've got a simulation running now. You can see that there's a kind of an alpha effect on the background. If I hit start, there's a fade down to the bottom there. So we're moving the X and Y coordinates in an animation. You saw the pop there with these boxes arriving. So we're moving basically the animations are based on changing parameters of the assets over time. So filling circles. This one's quite interesting. It's got two images on top of each other, which are moving across to kind of show a fill. So that's the application. What we've done is we've packaged up to go to the target, and in this configuration here, we're actually storing all the images in their pre-expanded form, so we're going to be using only 14K of memory over and above the heap and the frame size that we're using, so pretty lightweight. And what that means is that the images themselves are stored in Flash, so we're streaming them directly from Flash. So I'll show you the project itself. So we in IAR, let me hit play. If I stop that and restart it. So the application, if I hit run now, on the target board, I'll show you in operation. Okay. So the application itself is on the target. Where we're going to be loading and run. I've set a couple of breakpoints here. The first thing that happens is we're going to be running into the main, and the storyboard application actually is pretty simple to add to an existing application. So the main itself has all of the standard BSP components in there, and basically the drivers from the STM32 cube. So all of the BSP components that you're used to in the HAL and everything else is all standard code. So we build on top of that. We add our API libraries in the form of a set of add-ins, some .a files, some static libraries that you link with your application. We've got an abstraction layer here for the free RTOS link to Storyboard. So if you want to modify it the way that Storyboard runs with your target, that's what you can do. We give you the code for that as well. So I'll show you an operation now. It's just about to kick off and run. So this, if I show you the code again, so we're looking at something like 4 megabytes. So this is all of the images and assets stored on the target. So between 4 and 5 if you factor in the rest of the library code. So that's going to kick off and run on the target now. I'm just waiting for it to apply. You see the screen's just waiting. It's waiting for our code to run. So the first thing that's going to happen, we're going to hit main, and I'm actually using, you can see it in the background, a J-Link base here. So that I'm this strange arrangement at the top is it's a special type of debug connector which is fitted to this board. So I'm holding it in place with the elastic bands. So it's not very elegant, but there you go. It saves me holding it while I'm doing the demo. So if I just swap those around for 1 second, you'll be here. I am now in the main, and you can see that all we're doing is adding a task. So Storyboard main task. This is an application with a GUI needs to run asynchronously to whatever else is the target is doing. This is a worker task in this case, and I've created this just to blink some LEDs and basically load up the processor and create some time. So it's not actually doing a great deal, nothing useful at all apart from blinking the LEDs, but it's simulating what you would have as a kind of an application state machine. So I'll hit play now. First thing that's going to happen is going to run, and I'm going to load up that model, that storyboard model that we looked at before, which is here. If I go to the very top, so the storyboard stuff that we created in the beginning, we exported that as a header file, which is what we're looking at here. The first part of that is a binary representation of the model. And at the very end is basically a pseudo file system, a structure which represents these assets which are stored in there. You can see the image sizes are quite large. So these are the actual binary, uncompressed binaries, and they're stored in the form of a kind of a resource structure there. So that's the that's all created for you. So the first thing we do, once the application's run, it's going to start up and run. And the first thing it does is call back out into your application as the internal storyboard engine is initialized, and it's now calling out to initialize the display. So here you can add any code you like. This is, if I step into this, this is this display init and configuration of simple things like turning the LED on, initializing the parallel LCD interface in this case, and doing whatever else you need, even initializing the touchscreen now. So what we're also doing is adding maybe a second task, which is the input task. So Storyboard requires a kind of another asynchronous task to deal with any user input. So this is happening at any point. So you want to be able to run a task to scan touch input, maybe rotary encoders or any of the buttons that you like. So once that's initialized, Storyboard has been set up. It's personalized itself, the frame buffer locations, and also the sizing of the physical versus the actual frame buffer. So once the screen, you'll see the screen has gone black at the top. Once the screen has been rendered, you get a call out to display update, and this happens every time the screen is rendered or changed. So you can see there the first screen is gone and is hit back again. So running an animation at this point. So it's going to be refreshing quite often. I'm going to just let that run now. So you can see the application, and it looks okay. I can see here in real life it's a little bit notchy. So if I try and walk through, there's a touch response is a little bit limited there. So I'm not particularly happy with that. I'm going to touch on this. You can see the animation is very notchy. So things are happening, they're doing what they're supposed to, but it's not as smooth as I'd like. So some screens are worse than this. Is probably the worst screen. You can see here there's very notchy behavior, and the fill isn't looking very nice at all. So once that gets around to the end, I'm going to stop that, and okay, and I'll pause that and stop it. So what we want to do now is we want to start thinking about how we're going to do some analysis. So if I pop into Storyboard and run that again, actually I won't run it. I'll just flick the internal diagnostics on. So Storyboard itself has some built-in features. In our logger engine, we're able to capture performance metrics. So these are useful techniques to capture a lot of the internal Storyboard behaviors. I'm going to run that from startup. So in this case, on my desktop, and you can actually run this on the target. I'm going to run through the application quickly again. This time I'm collecting a whole load of internal statistics. Now this is fantastic from a Storyboard application perspective. However, it only gives us a Storyboard-centric view of the world. So it doesn't really have a lot of the detail about the diagnostics and the system dynamics. Actually, let me do that again, but at this time I'll just take some note of the performance log file. So it's going to log to a file. Oh, there you go, plog. So what I can do is open that. And what this is doing, this is kind of it's a Storyboard proprietary log that we've created. It dumps this in real time, and this is of course running on my desktop, but it gives a lot of detail about the internal performance of Storyboard. This is only part of the picture. We can look at the various screens, and we can drill down into some of the initialization and look at where the time's going. This column is time and duration. So very detailed analysis, and this is sort of stuff that we like customers to give us or to send us if they're having some issues and they need us to basically do some analysis and give them some recommendations. So you can see the different timings. There's 70 milliseconds to get to the start screen display. So and if I show that in graphical form, you can see yeah, it's pretty good. You can each of these segments here is when we transition between the screens, and you can see the CPU over, and performance over time. So that's very good from a Storyboard perspective. However, it doesn't really tell us a great deal about the target. So we need to consider some more details. So I'm going to turn on Tracealyzer. So I've added some code here, and I'll just hit build on that. And so what's going to happen is we're going to be bringing into play some of the Percepio code, which is linked in with my application. It's a small amount of code which is provided in source code form from the Percepio install. And there are two ways of doing this. The first one is use something called a snapshot mode. So remember, I'm using JLink here. So there's a JLink specific piece of code here. So snapshot basically is an on-demand kind of backtrace. So we have a rolling buffer, and you can hit play, and it's going to capture the last 500 milliseconds or however long your buffer is. In this case, what we're actually going to do is we're going to use a different mode, streaming mode, and I'll let the Percepio team talk in a lot more detail about this. But this uses a special mode of the Sega J-Link, which is called the RTT. Not exactly sure what that is, but it basically is a combination of software and hardware. And I've linked in the specific code for that and configured it onto the target. So what that's going to allow me to do is I'm going to basically use the hardware in the debugger alongside my application code to kind of capture real trace, but from a whole system perspective. So that's flashing now. Takes a little bit of time. Again, I think this is somewhere in the region of 5 megabytes when we deploy it to the target, and it includes all of the application assets that we mentioned before, and maybe 600 to 800K of storyboard runtime components. Now those are plug and playable. It depends what you need in your application. So just wait for that to come up. Okay, so I'm going to it's going to hit the breakpoints again, and I'll take those out and let it go. So the first thing that's happened now is it's going to breakpoint on our main, and there's a piece of code in here which is from the Percepio team, which enables the tracing in streaming mode. So it's going to hit that and wait any second. But first, let me make sure I've taken out the breakpoints, so we don't need that in the display init, and we don't need it in the storyboard application. Okay, so run. And you can see we're sat there and we're actually running, but we're blocked on the Percepio kind of trace tool connecting. So if I switch over to that now, what I'm going to do is going to start up a trace, live stream trace. And this connects to the debugger, and I'm going to start a session which will unblock. Let me move that down so you can actually see it. Okay, it's going to unblock the application. It'll start running. I'm going to start through the application and step through the screens just like I did before, but this time we're capturing a live streaming trace. Okay, so that's off and running now. You can see there. I'm going to run through the application. It's still performing pretty much as it did before, but this time we're capturing a whole load of runtime data on a blue screen. Okay, same notchy behavior. So what I've actually done is I've gone through the application and sprinkled a few trace points in there, which are what we call user events, and those will be used for the analysis later. So we got to the end of the session there, and I'll stop that. What I've done is created a trace. Now this has got a whole lot of detail. I'm going to leave the analysis to the Percepio team, and they'll be taking you through basically the analysis of the data we've collected, and I've already pre-shared this file with them. Okay, so we'll be taking it to the next level. So the idea really is to look at the system dynamics, understand why the system is behaving as it is. We're looking at analyzing some of the animation and performance, and then fine-tuning the touch. So I'll hand over to the Percepio team at this point.
With Tracealyzer, we can get a broad picture of the behavior at operating system level and drill down on any anomalies we find. This system runs an RTOS kernel that provides preemptive priority-based multitasking. This is an efficient and convenient way to handle multiple tasks in parallel, such as waiting for touch input while updating animations on the screen, and also responding to network messages, for instance. When using an RTOS, the tasks are essentially running as separate programs, ideally with one responsibility each. The RTOS kernel rapidly switches the executing task as needed, and this gives an illusion of parallel processing, even on single-core processors. Tracealyzer shows you exactly how the tasks are executed by the RTOS kernel, as seen here on the left. Each of these columns represent a task or an interrupt handler, and each of these solid rectangles are fragments of uninterrupted execution in between context switches. Note that the timeline is vertical. You can flip it to horizontal mode if you like, but the vertical mode has certain advantages. The vertical timeline allows us to show other events like RTOS API calls as labels on the timeline. This way we can get additional information about what the tasks are doing and how they are interacting. Tracealyzer captures the kernel calls automatically and also allows for adding your own custom events in the code, what we call user events. Crank have added such user events in the Storyboard engine, which allows us to see important UI events in the trace. We were seeing that the display was laggy, so let's take a look at that in Tracealyzer. This event is generated whenever the screen is updated. We can let Tracealyzer measure the time between these events by defining a custom interval. First, we give this a name, display update. Then we need to set a pattern to match and for the start and end, and we use the selected event for that. The intervals appear in the trace, but that's not interesting in this case. Now we select interval plot and our new dataset and get a graph over the durations of these intervals. So each data point here shows the time between the display updates. Here it looks pretty good, but if we scroll a bit and zoom out, we can see that there are quite substantial variations here. Most are 80 to about 150 milliseconds apart, and there was even some outlier of a few seconds, I think. If we double click on a data point, the trace view is focused on the corresponding point, and we can see what was going on there. This is a prime example of top-down workflow. We use overviews to spot anomalies and drill down to see the details. In the trace view, we can see that this task, worker task, was running a lot just before the display update was performed. This might have delayed the execution of the display update. This is quite likely because this system uses fixed priority scheduling, which is very common for RTOS-based applications. In fixed priority scheduling, a task doesn't get any processor time as long as a higher priority task is active. The benefit of this is complete control over the real-time behavior. The drawback is that the scheduling priorities of the tasks are critical for the application behavior and performance, and it's up to the application developer to find suitable priorities. In Tracealyzer, RTOS tasks are always ordered by the scheduling priority. In the trace view, the further right a task is shown, the higher priority. If we zoom out a bit, we can see that the worker task was running quite a lot. Let's take a look in the CPU load graph to get a better overview. Each bar in this graph corresponds to a section of the trace, and for each section we see how the processor time is distributed over the tasks. So this worker task is apparently using about 80% of the processor time. We also see that the total load is essentially 100%, basically no idle time here. This means that the lower priority tasks are using up all processor time that is available for them, so they don't get as much processor time as desired. There is also another user event logged by the Storyboard engine, the polling of touch input events. Let's check the time between the touch polling events using custom intervals like we did for the display update. First, we create the dataset. We give it a name and we set the patterns to match like before. And then we clone this interval plot and select the new dataset. Here we have even larger variations. This would certainly explain the laggy feeling in the touch input. This event occurs in the touch task, and you can see that it runs on even lower scheduling priority than the Storyboard engine task, which could explain the problem. Let's zoom in a bit so we see some more details. There are plenty of events here, so let's select this specific event. We also see this RTOS API call, vtask delay with the parameter 250, meaning that the task is suspending for 250 milliseconds. So it appears as the polling was only running at 4 Hz. This seems rather slow, so that could also explain it. But first, we need to fix the problem with the task priorities. There is no point in trying a faster poll rate if the task is not allowed to execute when desired. We need to increase the priority of the touch task. We can see that it has a very short execution time, so it should be possible to run this on quite high scheduling priority without interfering too much with the other tasks. And the worker task should have lower scheduling priority to avoid interfering with the touch task and the FreeRTOS timer task that Storyboard uses to schedule periodic events. I have already recorded a trace of this, so let's take a look. Okay, let's close these old windows. Let's begin by checking the CPU load. In the CPU load graph, we can now see that the task priorities are in different order, and we can see that the worker task and storyboard engine task now divides the processor time evenly. Before, the storyboard engine task was only getting about 20%, and now it gets about 50%. That should improve the UI performance quite a lot. Let's check the impact of this. We create a custom interval for the display update event like before. We give it a name and set the patterns to match. And we open it in the interval plot. Let's change the scale of the y-axis though. As mentioned, this shows the time between the display updates, and it seems that most are between 20 to 50 milliseconds. Before we made this change, the time between display updates and events was typically 80 to 150 milliseconds, so this clearly made a big difference. There are still some outliers, as the worker task is still running on higher priority than the storyboard engine task, but the worker task is no longer interfering with the timer task, and that's important. Let's check the poll touch event as well. We create a custom interval like before and show the interval plot. I'm hiding the intervals in the trace because the intervals are back to back, so they're not really interesting. Well, take a look at that. Perfectly stable. This since the task now runs on very high priority. And we have also been able to increase the polling rate to 20 milliseconds, 50 Hz, instead of just 4 Hz as before. So with this, we seem to have fixed the problems. There are lots of other things you can see with Tracealyzer, especially overviews that makes it easier to spot issues in long traces. You can see heap usage from dynamic memory allocation, stack usage, how the states of RTOS objects changes over time. You can plot arbitrary data from user events and much more. In total, Tracealyzer provides over 30 different perspectives and all works in this way, interactive and interconnected with other views. This allows for a top-down analysis where you spot anomalies in high-level overviews and then drill down to the detailed events to see the cause.
Okay, thanks. Oh, that's so awesome. Thanks, Johan. So just for completeness, I'll show you what I did. I took on the the suggestions from the analysis, and I've made a few changes here. So if I show you the first thing we did was change the priorities. So we were at 1 and 2 for the tasks. So worker was running at the highest priority task and was causing the disruption, as you saw. And the second thing was, we basically boosted the input priority. So the touch now is actually scanned at a higher level. It doesn't take much time, but we do it but at a high level than the rest of the system. And of course, the other thing was basically making a much more frequent check. So we're going to be polling much faster, 20 milliseconds here. So I've already flashed that, and if I switch over to the board and I'll let that run. Okay, so just for completeness, I'll show the applications it should be. Here we go, much smoother animation there. The pops are much more vibrant. Animation is pretty clear and smooth, so you can see the differences already. And this next screen here was the one that was showing up the highlighting thing. So we're still running everything in the system wanted to do, and we're getting a much smoother touch and UI. So you can see the insights that have been provided by a tool such as the Tracealyzer are really valuable, and it allows us to look at the system dynamics and tune them accordingly. So if I switch back to the presentation now. Okay. So in a recap, we basically took on some analysis and we balanced the system much more. We got the balance between the tasks running. The animations are much smoother, as you saw, and the fast touch response is much more evident. So you can see the power and the benefit of using these approaches with building user interface applications. And it's very hard to do this, without the full system view. So in summary, how Storyboard is designed to help you. It's there really to accelerate your development, and we've not shown a lot of it, but we do. Our design tool allows you to really get the simulation up and running on the desktop, run it on the target as soon as you can. We're encouraging iterations. Changing is, it doesn't require code changes. It's a UI model. And you saw here we're scaling down to the microprocessors. So we do run up to MPUs, up to other class of devices. So if you're looking at the MP1 and the STM32 MP1, for example, that's running Linux, and we're running on a high-level operating system. The design is the same, but the way that the tools are integrated is slightly different. And indeed, the Percepio tools are now available with Linux support. So perhaps in the next time we do this, we've shown you it running on a Storyboard running on more of an application processor environment with Linux. But that's something for the future. So I think I'll hand over to Scott at this point, and we'll wrap up and we'll do some key takeaways and take some questions. Over to you, Scott.
Thank you, Gary. Let me just get back to my screen again, and hopefully everybody now seeing my screen. Yep, perfect. So just some key takeaways from today. So definitely we do offer a 30-day trial, so definitely give it a try. Download Storyboard today. We, within our help center, have a variety of getting started videos and a wealth of information to kind of get your project going. Speaking of which, we also have a variety of different demo images that are specifically targeted to the ST boards, really allowing you to kind of kick the tires on the graphics capabilities of those boards to really allow you and speed up the evaluation process. So make them part of your evaluation process today. And then last but not least, check out Tracealyzer. As Johan mentioned, using the specific percepio.com/STM32 link, and you can check it out there and get some great information.